and push it, encourage it, can transfer to linear functions. So here's what I had in mind, Julie.
All right, thank you.
All right, so as you're thinking about this, I saw a lot of you were doing slope, right? And of course, we can just compute the slope, but we should stop for a minute and think about what the slope means. And what we're really saying is that there's a constant rate of change. Whether there is in reality or not, we're saying there is. And before we get into that, let's just talk about constant speed and see if you can get a little glimmer of how fractions play a role here. So to say something moves, if we go back to meaning, what do we mean by constant speed? Constant speed means that any distance traveled is in proportional correspondence with the amount of time it takes to travel that distance. Let me tell you what that means more clearly. What if I told you I traveled some distance in so much time, and then I asked you, how far did I go in half the time? You would say, half the distance. What if I did that and I went 3/4 of the time? I would have gone 3/4 of the distance. If there was a proportional correspondence and if there was a constant speed, right?
Right.
If there wasn't constant speed, this would be all the way out the window. But if there was a constant speed, if you travel some amount of time or some proportion of that, some fraction of that, you're going to travel a fraction of the distance. If the object travels d distance units in t time units at a constant speed, if it's a constant speed, then in a fraction of the time, you will move a fraction of the distance, including, what if I told you I traveled 5/3 the time? I'll go beyond of the 5/3 the distance. It works for all fractions. And proportional correspondence just means that if an object moves some distance in some amount of time, then any fraction of that time it moves the same fraction of the distance. Now in my, say, college algebra class, we spend a great deal of time just making sense of what we mean by constant speed because it plays such a role here. So, I don't know if you guys started with the graph, but in my classes I really push hard the thinking picture. Now a thinking picture isn't a fancy graph like this. A thinking picture looks like this. What are we keeping track of here? What are we keeping track of here?
Number of drinks.
2 drinks, point whatever it was. 6 drinks, point whatever it was. I just want them to have something to think about, you know? Not just go to the symbols that are so abstract, but to give them something concrete to think about. And what we're really searching for here is the formula for that linear function, right? So thinking picture, but of course I made it all pretty up here. So we're thinking about this, and what we know is from 2 drinks to 6 drinks, we know that the blood alcohol content increased by, who figured it out? 0.08, is it? 0.03? Maybe I have that. In an increase of 4 drinks, we increased the blood alcohol content by 0.083. Are you ready for this? Here it comes. Here comes the constant speed and the whole fraction thinking all connected right here. What we're going to do is we're going to cut up those 4 drinks into individual drinks. Now, if I told you that in 4 drinks my blood alcohol content increased by this much, then in 1 drink my blood alcohol content is going to go up by 1/4 as much. So if I cut this up into 4 parts, I got to cut this up into 4 parts. And how big would each part be? If I took that 0.083 and equally divided it among those 4 parts, how big would each part be? It would be whatever the constant speed is. Now it's not speed like distance and time, but it's a speed in the sense that for every unit of time, I'm going to have a proportional unit of blood alcohol content. And so here's how it might look. We don't just jump into the formulas. The students might go, well, let's see, if you initially started, now where are they initially? They're over here at the 0.025, right? Now, we know that we got to get this vertical intercept. So if you're here and you got to go back to the vertical intercept, how many copies of that constant rate of change do we have to go back?
2.
1, 2. I got to go back to 0 to get that vertical intercept. So I need 2 copies of the constant rate of change. And where did I start? 0.025. So I have to back up. I have to subtract 2 copies of the constant rate of change to get that initial quantity. Comes out to be that, based on the model. Now I know some of you are going to say, if you have no drinks, how do you get a negative BAC? That's a conversation for later. But this is the data I got. If you go to that defense drinkingdefense.com, that's what they said, so I gotta do it. All right, now, the blood alcohol content then is that initial amount plus how many copies of drinks are you going to make? The formula that we want is we're going to start here and we're going to copy the rate of change as many copies as we want. D copies of the constant rate of change. Initial amount was that. We have D copies of that. There's your formula. Now, about this time, my students here at community college always say, wait, isn't this that y equals mx plus b thing? And I just add dumb. Which is really easy. I just go, oh, what are you talking about? Y equals mx plus b? What's that? Because I want them to think about what all this stuff means. And I want them to have in their head, you start here, and you just add so many copies of that rate of change to see how your blood alcohol content behaves after so many drinks. And then, believe it or not, I try to get them to generalize them. Top of the heap. See if we can generalize. What if you know A, B, you know C, D? Write a recipe for finding a linear model for the situation. So what they do is they say, all right, now this is after lots of practice, you know, this isn't just like after one example. So they've worked through lots of things. But from here to here is how far? From here to there is how far? Well, from here to here would be C minus A. From there to there is D minus B. And what we're going to do is cut this up into so many parts. And if you cut this up into so many parts, each part will be 1 over C minus 8th of the time, or whatever it is. Therefore, I got to cut that up into 1 over C minus 8th of the distance. And then we have to have our initial value and do so many copies of that constant rate of change. And as you just generalize it, you get the general formula that you might recognize if we kind of clean it up a little bit. So, like Paul Lockhart would say, I don't start with the formula and then give them a bunch of exercises practicing the formula. We just build it and build it and build it. And at the end, we generalize and try to come up with convincing arguments. In fact, that's the final show you know. The final show you know is to generalize and come up with a recipe for finding linear functional formulas. And not all, but many can work their way through that. So in your packet, just so you know, you have a nice activity. I came home from school one day and my kids were watching Mythbusters, and I was so excited because they were talking about dodging the bullet. And in the episode, they're talking about, can you dodge a bullet? And if you flip over a page, oh, there it is, this page right here. In the show, this guy, who's this guy? I can't remember his name. Let me know.
Jamie.
That's Jamie. So Jamie is like with his finger drawing the axes. He's all right, we're going to keep track of time over here. Hey, look everybody, look where time is. Isn't that awesome? Time isn't independent. Time is dependent. I love it. Time is dependent, and the distance the gun is from the target is independent. And he says, look, they did in the video, you can see the video, they shoot the gun, they measure all the times, and he points here, and a little gunshot goes and makes the 1 point. And he points here, and another gunshot goes to make the other point. And they had, in this case, they had 3 points. And he goes, and look, it's a nice linear function. I don't know what he says. He says about linear. And then they don't actually find the formula, but that's what the activity is. Find a linear function formula for the time it takes for the bullet to hit its target. And then once you know the time it takes for the bullet to hit the target, then they find out, can you dodge the bullet in that amount of time? And so they have the other guy. Who's the other guy? Jamie and, I don't know. But the other guy is trying to dodge the bullet.
Adam.
And so Adam. And so we have some data there about how fast he can dodge a bullet. So if he can dodge the bullet in 0.790 milliseconds, well then how far away from the target could the gun be and he could still dodge the bullet? It's awesome. So you can work through this activity or use it in your class. And I do have, now you have to bring me a CD or something, but I do have all the video. But you know how Mythbusters, they kind of mix up the different things that they're doing in an hour show? I didn't want that. So I took the video and I cut it into 8 little pieces. No commercials, no mixing up. So I have all 8 little pieces. They're each like a couple minutes long. And so if you want to use this, you can actually show.
Cut them up.
Yeah.
And make
I
copies
cut
of
them up.
them.
I have 1/8 of the episode. So, and it's not overtime, so there you go. Of course, I have 4 hours of stuff and an hour and a half. There you go.
I hope the others in our book. Someone has figured out my job. Nice to meet you. Hey, bye, Scott. Good to see you. Bye, Susie. We'll talk to you later. This is why.
And they never tell me either. They never even tell me by the end of using their book,
Which one would you use?